All right. Good morning. So last week we started primarily the heat equation. We looked over several problems. One is to how to approximate the differential operators. And two is how much error does that approximation introduce. And three is how does that approximation error affect the solution. And at the end of last week, we started to look at a different type of equation. Instead of the heat equation, which is the first order derivative of time equal to a proportionality constant times a second derivative in space. We are looking at the advection equation now, which is the derivative of w to t plus advection velocity times the first order derivative is equal to 0. So that's the equation we are now looking at. We just want to go through the same procedure of deriving approximation errors and how does the error affect the solution. So we started with three different types of approximations. So the first type is forward difference. We're approximating the derivative using wi plus 1 minus wi divided by delta x. We can also flip it over and approximate it using wi minus 1 divided by delta x. And the third, we can take an average of these forward and backward derivatives. And the average gives us the central derivative. We also analyze the approximation error, which is defined as the numerical derivative minus the analytical derivative. And for the forward difference and backward difference, we see that the approximation error is order of delta x. So this is also order delta x. That means these two schemes are so-called first order schemes. First order means that there is no power on the delta x. If I shrink my delta x by a factor of 2, my error is also shrinking by a factor of 2. While the central difference, we get an error that is on the order of delta x squared, which means if you shrink delta x by a factor of 2, my error shrinks by a factor of 4, right? So that's a second order scheme. If you can afford a wider stencil, which means you want to introduce wi plus 2, wi minus 2, etc., you can potentially get third order and fourth order schemes, right? So we'll talk about how to do that also in the near future. Okay, so with this, we now get to the third question, is how does the approximation error affect the solution? Okay, so now let's switch to something a little bit more practical. Let's go to MATLAB and actually code up these schemes and see actually from our experience, how does the approximation error affect the solution? So let's switch over here. And in order to code it up in MATLAB, we first, again, we use OD45. So let's make a function and let's say forward, and we'll also make a function called backward and central. Okay, and let's see how it looks like. So we always want to return dw dt. And we are also not using time because the differential equation does not explicitly depend on time, right? So we also have w. So we want to just cross out this and figure out how to compute dw dt. So from the differential equation, we can move the u times dw dx to the right hand side. So dw dt by the differential equation just equals to minus u times dw dx. So that's what we are going to be computing. Okay, let's just move it down to here. So first we want to compute dw dx, and again let's do it in a periodic boundary condition. Okay, we still look at the periodic domain first. So dw dx, if we approximate it with the first derivative, we want to compute wi plus 1, right? Wi plus 1 would be equal to I want to concatenate W towards the right hand side. So from 2 to end and W1. So that's my Wi plus 1, right? So dW dx would be equal to Wi plus 1 minus W divided by delta x. And I didn't compute delta x. So here, let me say n is equal to length of W. And the delta x is equal to, let's also assume we have a periodic domain from 0 to 1. So 1 divided by n. Okay, so this would be different between periodic boundary conditions and non-periodic boundary conditions. If you have non-periodic boundary conditions, then depending on your boundary condition, the number of unknowns may be n minus 1, maybe n, or even n plus 1 if you have no boundary conditions. Okay, so here we go. Now my dw dt would be equal to minus u times dw dx. So let's set a u over here. First, let's consider a u that moves. Well, let me actually set a global u here so that we can set our u over here. Okay, and let's say u is equal to 1 for now. So this global variable is going to be passed into this function. All right. Okay. So what kind of initial condition do we want? Well, here we actually can have any initial condition because the analytical solution, unlike the heat equation, is actually known for any type of initial condition, right? So we have the solution, we have the analytical solution to compare with. W of x and t would always be equal to W0 x minus ut, right? So as soon as we know the initial condition, we know what to compare. And particularly if we have a periodic boundary condition and have a domain length equal to 1, that means if we have a periodic in 0 and 1 and ut is equal to 1, that means my wxt is actually equal to w0 of x, right? I recover the initial condition. Because if you look at the wave has moved across the domain for a whole period. So that's a very good initial condition. That's a very good solution we can compare our numerical scheme against. Okay, so that's the benchmark. Any questions? No? Okay, so let's actually just provide the initial condition that's a square wave. 0, 1, and let the square wave to be, let's actually make a square wave like that. Let's say from x, let's set x from a third to 2/3 to be equal to 1 and the rest of them to be 0, okay? So let's code up our initial condition here. So W0, so let's say x is equal to, well, let's set an n first. Last time we started with n equal to 10, and this time let's do it a little bit more. So let's make 100, all right? So my x would be linear space of 0, 1, n plus 1, because here I have n unknowns, but I have a periodic boundary condition. So there have to be a duplicate point between 0 and 1, right? W0 is equal to W1. So there is one less unknown than the number of grid points. So I make a grid point, n plus 1 grid points. So that's my x. My W0 would be equal to zeros, n, and 1. Okay? Actually, let's make it n plus 1 and 1 to match x. And we want to set the middle third to be 1. So W0 parentheses. So let's say x greater than 1/3. Let's set it to 1. And then again, 2/3 greater than 2/3. Let's set it to 0. So if you plot now x and the W0, the solution is what we wanted, right? So we have a square wave. Okay. Now let's plug this into ODE45. T and W would be ODE45. I have a forward difference function. I just code it up, and if u is equal to 1, I want to solve it between time 0 to 1 so that the wave advects over a single period. And w0, 1 to n minus 1 is going to be my initial condition, right? Because I want to ignore the point on the very right. The point on the very right is actually equal to the point on the very left. So, okay, what did I must have forget to put in one of these. Yes, okay, so that's fine. The solution should still be good. So now if you look at the workspace, we can see OD45 take about 1,000 time steps, and the final solution, I called it W, is the number of time steps times the number of unknowns. So let's plot the final solution to see what it looks like. Before we plot the final solution, let's plot the initial condition first. Okay, so which is this, and let's hold on and plot what the final solution is like. So the final solution is W and the last time step, all the spatial points, together with so now that's 1 by 100, so it's a row vector. So W and 1, right? Let's plot it in red. All right. So what is it? It looks like I have a solution that is 10 to the 85, right? So what is happening here? It's divergent, right? So that's the situation that in the analysis of stability we did not see in the heat equation, but we do see that now in advection equation.